recording in cloud, and later I will share it. Okay. So today we are going to learn Poisson regression. So what is the outline of the lecture today? So I am going to discuss five different topics. First of all, what is simple and multiple regression? And their limitation. These are the things I am going to discuss first. What is the simple and multiple regressions and their limitation? You can see from the back. Okay. And after that, I will discuss what is binomial distribution, how it come into an existence. Second topic is what is binomial distribution, how it come into an existence. Third one is Poisson distribution. Where did it come from? Okay. After that, I want to derive the regression. This is third one. Then fourth one, I want to derive Poisson regression. Derive Poisson regression. And finally, fifth one, application, real life example. Real life example or application by R. These are the five main topics. It will take me almost 2 hours 30 minutes or 2 hours 45 minutes. Okay. So let me start. What is simple and multiple regression? So 1805, his name is Galton. He added a arrow term to a linear equation. Everyone know about this linear equation, y equal to beta 0 plus beta 1 x. This is linear equation where beta 0 is the intercept, beta 1 is the slope. Slope means rate or change of rate. Okay. And 1805, Dr. Galton, he added a term known as the arrow term with this model, and he put here like this. Also put the suffix I, N. And then he said that this is a now linear model. Understand? 1805, he proposed these things. He not only proposed, he also further discussed how to estimate beta 0 and beta 1. Okay? So now everyone in this classroom, if I ask, maybe few of you who already took classes, they already know. If I ask you 2x1 plus 3x2 equal to 5, and then x1 plus 7x2 equal to 3. If I ask you to solve these equations, each and everyone will say that there is a solution for this system of linear equations where x1 and x2 will have a value, right? This is a system of linear equations, but there is two unknown. If I ask you further these questions by adding this, suppose 7x3 and then 8x3. Understand? Now I added one more variable. Understand? How many solutions are in there for x1 and x2 and x3? Previously, two unknown, two equations, right? Finite number of solution, right? Two unknown. Now there are three unknown and two equations. How can you solve that? Is there a unique solution? No. One of these you have to assume. And based on that assumptions, there is a multiple solutions, right? Infinitely many solutions, right? Okay. So now you understand these things. Two unknown, two equations, you can get the finite solution, finite number of solutions. If there are two equations and 3 unknown, infinitely many solutions. You understand this, right? But now suppose you have this type of problem. What is that? You have this type of problem. X1 plus 7x2 equal to 3. 2x1 plus 8x3 equal to 2. And then 3x1 plus 9x2 equal to 5. And then 4x1 plus 7x2 equal to 8. So how many equations are in there now? And how many unknowns? I want to use all of these equations to estimate the unknowns. Are you understanding? I want to use all of this equation to estimate unknown. This is what Galton came up with the idea when there is a y1, beta 0, beta 1, x1 plus e1, y2, beta 0, beta 2, x2 plus e2, and then yn, beta 0, beta 2, beta 1, x, x1, x2, xn plus en. Are you seeing how many unknowns? 2 unknowns, right? Beta 0 and beta 1, right? 2 unknowns. And how many equations? Many equations, right? But we have to use all of this information to estimate beta 0 and beta 1. That method is known as the least square method developed by him. Clear, right? Are you understanding, right? Are you understanding? So Galton developed these simple linear regressions in 1805. And then this is the way, like by minimizing error. How can we estimate these things? We can estimate these things error equal to this yi minus beta 0 minus beta 1 xi. So we write like this way. Then we take the square on both sides. And then we take the summation, sum of squares of residuals. We call this residual yi minus beta 0 minus beta xi square, like this. And then they differentiate it with respect to beta 0 and beta 1. And then they find the solution for beta 0 and beta 1. In such a cases, all given informations are used, x and y. Understand, right? This is what known as the least square method. Least square method. So I have given you first system of linear equations with the 2 unknown, and then ask you if there will be 3 unknown and 2 equations, and then I come and then I show you if how can you incorporate all of these equations to estimate beta 0 and beta 1, right? If you just simply write the equations, all of these 10, 20 equations, and ask any graduate students, they know all of these things, but they cannot think the way I am discussing. You understand, right, what I said? Suddenly, if they know all of these things, but it will not immediately hit to their brain. How can I use all of these informations to estimate beta 0 and beta 1? So what is the limitations of these simple or multiple linear equations? There are some limitations. Beta 0, beta 1, suppose x I1 plus beta 2, x I2, and then I want to go beta k, x ik, and plus arrow term. Okay. So there are some limitations for this. So one of the assumptions of this multiple linear regression model is that response variable y must follow normal distributions with mean x beta and variance sigma square. This is the assumption. Y must follow normal distributions. This model in the matrix form can be written as y equal to x beta plus epsilon or e. Okay. So y must follow this. And then there is an assumption, distributional assumption. EI follow normal distribution with 0 mean, standard deviation 1 or sigma square. Sigma square. And yi and ei only has the distribution in location parameter. Their dispersion parameter is the same, sigma square. And normal distribution y is a normal distribution. This follow Gaussian distribution and normal distribution. That means quantitative variable. In most cases, it is called also continuous variable. Understand? So what is the main limitations, violation? Suppose Y is a count data. Count data. So what do you mean by count data? Number of accidents. You can compute, right? Number of accidents, 7 accidents, 5 accidents, 8 accidents, right? You can compute. And the number of phone calls, which you can compute. You cannot say 3.5 phone calls or 19.7 accidents. Can you say that? No, right? So count data. If your data is count data, in such a cases, this regression is not appropriate because count data follow different type of distributions. Count data follow Poisson distributions, negative binomial distributions. Clear? Normal distribution is not followed by the count data. Number of COVID patients, number of phone call, number of traffic accidents, all of this. Clear, right? So this Y is a count data. When Y is a count data, we cannot use multiple linear regressions that I just mentioned. We have to use Poisson regression. Okay? We have to use Poisson regression. So how can I write Poisson regression in this beautiful format? I want to write Poisson regression. This is a multiple linear regression model where response variable is a quantity follow normal distributions. How can I write Poisson distributions regression format in this format? That is the challenge now. Are you understanding? Now we have to write like this. So let me write Poisson distributions. This is the Poisson distribution. This is the Poisson distribution. Where x takes value 0, 1, 2, up to infinity. Now you can ask me what is Poisson distribution, how this come into an existence. If this is your questions, next 10 minutes I'm going to answer that, maybe next 15-20 minutes. Okay. This is a PMF. PMF means probability mass function. Probability mass function are for discrete random variable. Probability mass function are for discrete random variable. Discrete random variable means the variable that can take discrete number. Okay. Discrete random variable. So what is the condition that a function will be a probability mass function? It must satisfy two characteristics. Number one, function itself is always greater equal to 0. Number two, sum of the probability function equal to 1. Okay. These are the two characteristics. If any functions satisfy these two characteristics, we can say them either probability mass function or probability density function. Density function is for the continuous variable. Mass function is for the discrete variable. Okay. So this is a Poisson. So now you can ask me question, how someone give this Poisson distribution? Did you wake up in the morning and write a function and check these two properties and then he is claiming that this is a Poisson distribution? Someone wake up in the morning and wrote a function and these two characteristics are satisfied, then he is saying, and then all other people on the planet, they are agreeing with that, well, we will accept these things as a Poisson distributions because you did it, you are a very famous mathematician or something like that. No, this is a derivation. This is derived from binomial distribution. Understand? So next 20 minutes, I'm going to talk about how these distributions come into an existence. Okay. Suppose we have 4 coins tossing experiment. I want to conduct 4 coin tossing experiment. I want to conduct. Okay. So if I put here 2 coin, HH, HT, TH, TT, here is 2 coin. And here I want to put another 2 coin, HH, HT, TH, and TT. And then I can write here HH, This is a sample space for 2 coin tossing experiment. If you toss 4 coins, you will end up with 16 sample points, right? 16 sample points. So now if I want to compute these things, x equal to number of heads. Okay? X equal to number of heads. Then if I want to write probability of x equal to 0 equal to 1 over 16, because there are 0 head only one sample point. Probability of x equal to 1, there are 4 over 16 sample point. If probability of x equal to 2, there are 6 over 16 sample point. And then probability of x equal to 3, 4 over 16 sample point. Probability of x equal to 4, 1 over 16. Do you agree with that? X equal to number of heads, right? I can easily compute these things. Now someone is walking in the corridor. He said that, well, there is a 4 coin tossing experiment. So that is where you can find this probability. How can we find this probability if I want to toss the coin 10 times? Okay. If someone asks me who is walking in the corridor, he listened to my lecture. He said that I want to toss the coin 10 times. Then his further question is, I can say that if you toss the coin 10 times, then that is the number of coins. Let me check quickly. 10 equal to 1000. One 1032. Is this 1032? 1024. Okay. So do you understand my question? So someone wants to compute probabilities of getting 7 head by tossing a coin. This is 2, and then I have to put there 1024. 1024. So 1024, right? How many sample points? 1024 sample points, right? If you toss the coin 10 times. Now, if you want to compute like probability of 7 head, you have to construct the entire sample points. It will take how many? Maybe 2 days, 3 days, right? Right? But fortunately, like if you go to the MIT or Stanford, like university top scientists, they say always one thing. For some reason, there is always a formula to compute something. For some reason, they say these things. I heard the lectures. They said that either it is already discovered or it is yet to be discovered. The top scientists who are doing research like in different level, high level, they said there are some kind of formula is in there. So in order to solve this problem, the scientists, they come up with a binomial distributions problem. Okay, take a look at that. If I write like this one in this formula, x equal to 0, I am tossing the coin 4 times, probability of getting 0 head, and probability of appearing head is this, and probability of appearing head is 4 minus 0. So if you compute this thing, this is 1 over 16. And similarly, probability of x equal to 1, you are doing it 4c1 half to the power 1, 1 minus half to the power 4 minus 1, which will give you 4 over 16. And then if you write here probability of x equal to 2, 4c2 half to the power 2, 1 minus half to the power 4 minus 2, which is equal to 16. Four head, equal to this 4C4 half to the power 4, 1 minus half to the power 4 minus 4 equal to 116. Understand? So by method of induction, it make a I can take the decision by method of induction. See, I construct a sample space. I computed the probability in the left side by looking at the sample space. Here I computed everything by using the formula. Understand? So now we have a formula. What is the formula? If n equal to number of trials, a hospital has a 100 patients. Understand? Number of trials. So n equal to 100. And then x equal to number of successes. Okay. And p is the probability of success. Then we can write probability of a specific number of successes and Cx p to the power x 1 minus p to the power n minus x under the condition that x takes value 0, 1, 2 up to n. I toss the coin 10 times, I can get 10 head. I toss the coin 10 times, I got 0 head. So this is the range. And what are the condition in here? P is a probability, it must be greater or equal to 0. So this is intuitively you can think, right? By comparing these two things, by looking at this sample space and this probability and their corresponding mathematical formula, you can come up with this general formula for the binomial distribution. Everyone is okay? Everyone understanding? Okay. So this is called the binomial distribution. This distribution has a mean. I don't want to derive these things because if I derive these things, it will take another 15 minutes and it has a variance. Variance of binomial distribution is NP 1 minus P. The rationale for deriving these binomial distributions, because I am now moving to Poisson distributions from these binomial distributions. Understand? Didn't I say that one intelligent guy wake up in the morning and he write the equations and formula and immediately said that, well, these things satisfy my two characteristics for being a function to become a probability density function. It did not happen that way. It come into an existence by mathematical derivation from binomial distributions. Okay, that derivations now I'm going to show you. After derive the Poisson distributions, then we will move to regressions. We will formulate all of these in a regression format. Okay. Now take a look at that. This is our binomial distribution and Cx p to the power x 1 minus p to the power n minus x. Okay. On these distributions, we will do two operations. Two operation we will do. And that those operations are realistics. Those operations are realistic operations. What are these? Number one, we consider lambda equal to NP. Are you seeing NP equal to what? NP is the mean of the binomial distributions. So I am assuming lambda is a thing that is equal to NP. And then number two, I want to consider n goes to infinity. Okay. Under these two assumptions or two realistic mathematical operation, if we apply over there, then we will end up with a Poisson distributions. These two operations also apply P tends to 0. Why? Because from there, if I compute probability equal to lambda over n, right? If n goes to infinity, probability goes to 0, right? This is very realistic, right? Real life example. in the Macomb Childler Park, how many accidents takes place every day? Almost zero, right? How many car passes by that intersections every day? Maybe 100,000. Are you understanding? So in your cell phone, how many times calls are dropped? You got maybe 100 times, you got maybe 1 or 2 times. So probability of call drop is very small, right? Probability of traffic accidents is very small, right? How many cars are passing? 100,000, right? You understand? This real life example is matching with this mathematical notation. Are you understanding? These mathematical notations with the real life example are matching, right? So let us do the operation now. So in order to do the operation, let me write it. So my purpose from these binomial distributions, I want to end up with these things. I want to end up with this. Okay. After ending up with this, then you will be satisfied that, well, Poisson distribution is nothing. It is just a derivations from binomial distributions where n takes large value, that means n tends to infinity, and lambda equal to np. Understand? Lambda equal to np. So lambda equal to np, there is another rationale. Lambda is a mean, and then lambda is a mean, and np is a mean. In those regression, we are actually fitting the average line, right? You understand? In these regressions, we are always fitting average line, right? And you have seen np is the mean of the binomial distributions, and I am assuming lambda equal to np. That lambda will exist in the derived Poisson distributions, and on that lambda I will fit the regression. Understanding, right? So regressions that you are saying is always average, unless if you use the quantile regressions, which you will learn maybe in the 7th week. Quantile regressions, that is what you can feed the line on different percentiles of your distributions. Okay. Probability of x equal to ncx p to the power x 1 minus p to the power n minus x. Now ncx could be written as factorial n, factorial x, n minus x. Factorial. And then p could be written as lambda over n to the power x and 1 minus lambda to the power n over n minus x. This is the way you can write all of your term. Okay. So from there, anyone has any question? No question, right? So where I am going now, I want to derive Poisson distribution from binomial distributions. So if I want to write it in here, n minus 1, n minus 2, and all the way n minus x plus 1, and then I will have n minus x factorial. That is coming from the numerator part. And denominator part, I have factorial x, n minus x factorial. This is what I have. I want to cancel this. Lambda to the power x, n to the power x, 1 minus lambda over n to the power n, 1 minus lambda to the power n over minus x. Okay, now I want to make this quantity equal to 1. This quantity equal to 1. Okay, now take a look at that. I want to put here n over n, and then n minus 1 over n, and then n minus 2 over n, and then n minus x plus 1 over n. So how many n are in there? 1, 2, up to n minus 1 in n minus 1 n in there, n minus 1 in, and then with this n. So n to the power x, that is matching with this. Are you understanding? No? Okay. How many n in here? 2, right? So if you continue in here, n minus 1 n in there. Okay, and with this one. So in here, sorry, I said n minus 1, not n minus 1. N minus x plus 1. So that means n with this one, there will be n to the power x, this and that. So that is why I bring one n under there, another n under there, another n under there, another n under there. This is exhausted with that. If you don't believe, then just put n equal to maybe 5. Put here n equal to 5. If you could put n equal to 5, how many you are getting here? 4, right? Put here n equal x. Put here x equal to 5. If you put x equal to 5, n minus 4, right? N minus 4, how many n then? 5 more. And then this is a 5, right? Not clear? Okay. Take a look at in there. I want to put there. Okay. If you do not understand, just give your attention in there. I want to put x equal to 5. If I put x equal to 5, what I get? N minus 1, n minus 2, n minus 3, and n minus 4, right? I will stop there, right? Right? And then I put x equal to what? 5, right? Got it now? So now 1, 2, 3, 4, 5. There is 5. Clear, right? Okay. If you are clear on that one, let me vanish this thing first. Okay. So how can I do that? This is cancelled out. This is 1 minus 1 over n. This is 1 minus 2 over n. And this is 1 minus x minus 1 over n. Clear? Clear, right? This one is clear, right? Now, if you do here, what did I say? N goes to infinity, right? Didn't I say n goes to infinity? Now, if you put here limit n goes to infinity, then what will happen? This term equal to what? If n goes to infinity, then this term equal to what? 1. If n goes to infinity, this is 0, this is 0, this is 0, this is just 1, right? Are you understanding? So down the road, rest of the semester, all the regressions models that I'm going to discuss, Cox regressions, lasso regression, negative binomial regression, elastic net, and then Ries regressions, quantile regression, all of this mathematically, I will derive all of these things and show you the rationale why they come into an existence, how, and then after doing these things, then I will show you real life example. So that part is gone. Okay. So then what is remaining from there? From there, we have now lambda to the power x and factorial x. And then we have this part remaining, 1 minus lambda over n to the power n. And then we have 1 minus lambda over n to the power minus x, right? Okay. See, we already got 66% of our desired Poisson model. Lambda to the power x over factorial x. Take a look, 66%. Lambda to the power x divided by factorial x, right? Now we have to bring e to the power minus lambda. We have to bring e to the power minus lambda from these two quantity. From these two quantity, we have to make e to the power minus lambda. Okay, how? Take a look at that. So we want to do this one. Suppose this is one I want to consider as A. I want to consider this one as A, and that one I want to consider as a B. Okay. Now let's do the operations. a equal to 1 minus lambda to the power n to the power n. Okay. So now if you take a log of a, then what are you getting? N log of 1 minus lambda over n. Just easy. And then logarithm series is this. This is the logarithm series 1 minus x. Understand? 1 minus x, that this is called log of 1 minus x. This is x. That x must be less than 1. Otherwise, log cannot handle negative value. Log cannot handle 1. Log cannot handle 0. Okay. This it will explode. And by force, this is less than 1 because n always bigger than lambda. Okay. So now, if you multiply this with that, what are you getting? Minus lambda you are getting. If you multiply this, then you are getting lambda over twice n. If you multiply this, you are getting lambda cube over 3 n square, like this. Clear? So each part has an n, right? Denominator has an n, right? And n goes to, so that means rest of the part is 0, right? So you have what? If you take limit n goes to infinity a, then you will have minus lambda, rest of the part will become 0. So then what you will have? A equal to what? To the power minus lambda. So I got e to the power minus lambda, right? Now I have to show that this quantity equal to 1. That is easy. So now the other quantity, if you take, suppose b equal to 1 minus lambda over n to the power minus x, right? Minus x. Right? Minus x. So if I take here b to the power, suppose I want to take here b to the power minus 1x. If I take here b to the power minus 1x, then it will be 1 minus like this, right? And that part is going to be 0, right? And after that part, if you put here limit n goes to infinity, b to the power 1 over x equal to 1. And that part will be 0, right? That part will be 0. Now, if you transfer it back, if you want to transfer it back, b equal to, like, I do not need infinity anymore. B equal to 1 to the power minus x, right? 1 to the power anything, whatever you put, is always 1. Either negative or positive, whatever you put, that is always 1, right? 1 to the power negative 100, 1 to the power positive 100, 1 to the power anything that you want to put, it is equal to 1. So it is proved that Poisson distribution is actually a derivations from the binomial distribution under two conditions, and that means number of trials, that means number of car passes in a particular traffic intersection in a day is infinity, huge, okay, and the probability of having an accident is low, right? So that is the realistic things that come to the people's mind, and they like to do some math operations, this and that. That's the reason they come up with these derivations. Okay. So what we have finally, this is our binomial distribution. This is our binomial distribution. From there, after these operations when we made, and n goes to infinity, we come up with a new distributions. The name of the distribution is e to the power minus lambda, lambda to the power x over factorial x. Okay. So what is the applications for this? Application is that when number of trials is very high and the probability of happening an event is very low, then we can use these Poisson distributions. So now Poisson distribution number of accidents is a count data. Number of accidents or number of phone calls. These are all count data. Count data. So as these are count data, now we want to incorporate all of these things to a regression format, and then we will estimate the parameter. Ready? So far so good. Any question, comments, problem, personal problem that you do not want to share? Okay, so let me start the derivations like the Poisson regression derivations. So in the Poisson regression derivation, let me derive these things, then I will discuss what is Newton-Raphson method. Because without Newton-Raphson methods, parameter cannot be estimated analytically. There is a two words, remember. Analytical solution, numerical solutions. Analytical solution means very beautiful mathematical formula, mathematical expression is in there. That is called the analytical. Understand? Very beautiful mathematical analytical solutions. Like the simple and multiple regressions, you have all of them seen this type of solutions, right? Right? This is called the analytical. You use all the mathematical analytics and then come up with these solutions. In this one, we would not have a very beautiful analytical solutions. We will have a numerical solutions on the Hessian matrix. And then on that Hessian matrix, we will apply Newton-Raphson method to get a solutions. One of the limitations of the Newton-Raphson method is that initial guess. If initial guess is very bad, in that case, you might end up with a wrong solutions. Are you understanding? For example, USA GDP is in $1 trillion, right? But if you want to estimate the GDP of a Southeast Asian small country like Bhutan or Nepal or my country, Bangladesh, and then there is a GDP data, you are going to do something, and the initial guess you are putting in that $1 trillion, but their economy is $1 billion, maybe $50 billion. But you put here $1 trillion. So that means the initial guess is very bad. Right? Okay. So now, in order to start derivations for the Poisson distributions, if you have these things, y, you sometimes take log of y, right? In the regressions, you sometimes take log of y. Why? The data is skewed, but if you take the logarithm, then data become normal, right? Okay. So now we have a lambda. Lambda is what? Lambda is the mean of the Poisson distributions. Okay. Quickly derive this. It will take maybe 1 minute. To the power minus lambda, lambda to the power x over factorial x. X goes 0, 1, 2, up to infinity. I want to find the mean of these distributions. X, which is the expected value. X takes value 0 to infinity. And then if you take 1 out from there, e to the power minus lambda, and you have a x, then lambda to the power x minus 1, then x into x minus 1. This and that cancel, x equal to now 1 to infinity. Because previously it was starting from 0. As you are cancelling out 1, as you are taking 1 out, so the range changes. Okay. If you do not change the range, that means you are exploding it, right? If you plug here 0, what will happen? If you now plug here 0, then what will happen? Negative infinity, right? It will not work. Okay, so in this case, e to the power minus lambda, and then if you plug the value x equal to 1, then you will get here 1 And then if you put x equal to 2, lambda over factorial 1, x equal to 3, lambda square over factorial 2, like this. This is nothing but the exponential series, right? To the power minus lambda, lambda, and to the power lambda. And this is the lambda. So mean of the Poisson distribution is lambda, which I have mathematically derived. Okay, mathematically derived. So this is the exponential series. This is the definition. This is the definitions. People defined it. Square by factorial 2, x cubed by factorial 3, x4 by factorial 4. This is gone. Okay. So before the inventions of this calculator, there was a book, log book. In that log book, there is also the, if you plug 1, whatever value you will get from there, that is e power 1. If you plug 2, whatever value, 3, 4, 5. I have seen that book. Okay, exponential. But now computer is there, we can do this. Okay. So you have seen this is the mean of the Poisson distribution. This is the mean of the Poisson distribution, right? And all the regressions focuses on average, on mean, unless it is quantile regression. Okay, all the regressions. So we will put everything on this lambda, like betas and then covariate x, all will be expressed in terms of this lambda. Okay, so now I want to write like this: a log of lambda. Log of lambda could be written like this: beta 0. Now I have to look it in there. Beta 1 x 1 I, beta 2 x twice I, and then beta p x pi x pi, something like this, or ip, and which could be written as actually I1 and I2 and IP. That is better explanations, but anyway, I have uploaded all of these lecture materials, handwritten derivations, everything is in the Western Online. Okay, all of this in the Western Online. So if there is a abuse of notations or I am writing different notations, so don't feel bad. The correct notation and correct derivations is already in the Western Online. So now this is would be written as j goes 1 to p. J goes 1 to p. Now, if I want to write here lambda, then it is nothing but exponentiation of this quantity, beta 0, beta 1. Let me rewrite this things x I1. Okay. And I want to our dependent variable, response variable y, that follow Poisson's distributions with parameter lambda. This is the Poisson distribution. Our response variable y that follow Poisson distribution with parameter lambda. Now, likelihood function of the Poisson distributions. Likelihood function of the Poisson distributions can be determined like this: I goes 1 to n, and e to the power minus lambda, and lambda to the power y I divided by factorial yn. That is the likelihood function. R.A. Fisher, he come up with these things. When people was giving probability distributions, these distributions, all of these distributions was given. Some of these distributions are given maybe 200 years ago, 300, 400 years ago. But how to estimate the parameter, there was no unique way. People are unable to discuss or develop those things. Okay, this all was developed in 1920, 1930, something like that. First statistics department opened in England in 1905, and USA first statistics department in 1934 or 35, George Washington University, and then Iowa State University. R.A. Fisher came multiple times. Okay. I am a student of a student R.A. Fisher. I'm a last student of a R.A. Fisher student. Okay, so he said that before maximum likelihood estimations, people estimated parameter by using method of moments. But R. Fisher gave this method to estimate this. Okay. So this is a maximum likelihood. Now, if I want to take a log of this, then log of L would be written as small l equal to sum of yi log of lambda, and then minus lambda, and then minus log of yi. If you take the logarithm of this one, you will end up with this. If you take the logarithm on this, okay? Logarithm, if you take the logarithm on this, you will get this log. After doing that, now if you do some value, if you plug in there, then you will get what? Are you saying this log lambda equal to that? So I can plug that thing in there, right? This log lambda equal to that one I can plug, right? So I can plug it in there, which is equal to yi. Here it is gone from, here it is gone from j, here it is goes from n. Then I can put here j goes 1 to p, and then beta z x I z. And then I put here the value of the lambda, which is equal to lambda equal to like this. That one, which I can put e to the power sum of beta j x I j, and it is j goes 1 to p. And that is my log of y. You see that? I have Poisson distribution. I find the likelihood function in the Poisson distribution, and Poisson distribution has the parameter lambda. Lambda is the mean. Mean is the function of the covariate and the parameter, right? Poisson distribution has a parameter lambda. Lambda is the mean, and then on that mean, I'm doing the parameter covariate combined with the parameter, linear combinations of the covariate with the parameters. So that's the likelihood function. Now I will do the first derivative and then second derivative. Hessian matrix we will construct, and then from Hessian matrix we will go Newton-Raphson method to estimates. Okay, let us do some derivations in here, some differentiation in here. If we derive these things with respect to specific beta, see, when we do the differentiation, we will do the partial derivative by targeting each parameter. Beta 1, so we differentiate it del beta 1. Others, so partial derivative we have to conduct in here. So let us do these things del beta, and if I plug equal to 0, first order derivative equal to 0, I am plugging. Then what I am getting in here? I am getting in here xim, because this xim is beta m, here is beta m. So if there is beta m, this is also im. So that is why this xim. And then beta is gone, because beta m is in differentiating out. We differentiated it out, and then we have this yi in here. Yi in here, I goes 1 to n. This yi in here, and then we will have again differentiation in here, which is equal to e to the power sum beta j x I j, and then here we are computing over this. Now take a look at that. Let me explain these things here. So suppose ddx of e to the power 5x. If you differentiate this, then what you will get? E to the power 5x times 5, right? You got this one, right? That 5, because of this 5. Here I have a xn. That xn is in here. This is, so one xn coming from I am in the another one coming from there. So that is why the equations looks like in this format. Okay. So that is our main equations. I can call it number 2, equation number 2. After that, now equation 2 will be solved numerically by using Newton-Raphson method. So equation so they gave this formula like almost 400 years ago, and lot of applications of this. A lot. So only limitations of this initial guess is very bad, and your results may not be stable. I will show how the Newton-Raphson method works in a small graphical example as well as numerical example. It's so beautiful graphical example one. Okay, so after that, if you take the second derivative, your second derivative is this one, and d beta m beta L. If you do these things, then you will end up with this XIM, XIL, then to the power beta JX IJ is go E regression, and here is I want to. That's the way. So, and then after that, our Hessian matrix is obtained, which is called like the second order derivative of each parameters. Then diagonal one will give you variance, and the off diagonal will give you covariance, something like that, in order to compute those things. Thank you very much. So now let me derive little bit more about how these diagonal element and off diagonal elements are needed to get not only the estimates and also the covariance of the regression parameter betas. So this is the finally variance covariance matrix element could be obtained from there. What is X? X I'm going to define in this format. X equal to and what is W? W is diagonal elements. So then they find like second order derivative that I mentioned in there in terms of X and W. This X and W, they find the second order derivative, this one. Then it is easier to compute all of those things from the matrix. Okay, let me give you the example of Newton-Raphson method, because in this case there is no unique solution. So Unique solutions can be obtained after differentiating if you get a very simple equations which is equal to 0, and then you do some left and right hand transformations and get the parameter value. But if parameter and variable, all of them are entangled, all of them are combined in such a way that you inseparable way. You understand that? Inseparable. They cannot be separated, and you end up with a very beautiful analytic solutions. In such a cases, algorithm needs to be run, and you will end up with a solutions that is numerically stable. Now I am going to discuss a very beautiful Newton-Raphson method by a simple example. Newton-Raphson method. So what Newton and Raphson said that to find the root of a continuous and differentiable function. Differentiable function fx at x equal to x0 the Newton-Raphson method tells us that better approximations can be obtained by this x0 is your initial guess. Okay. You have an equation. I will give you numerical examples. This x1 will be you have a function fx. You have a function fx. What value of x will satisfy the function? Okay. Your function is suppose 5x square 9x plus 10 equal to 0. What value of x will satisfy that equation? Understand? So this is called the, so you have to find the initial guess, and then by using this we will update this. After certain iterations, certain number of iterations, 5, 6, and 7 or 8, 9 times, after that many times of iteration, you will get previous iteration and current iteration is giving almost the same level. So you say that this will be my solution. Understand? Newton-Raphson. So now again, why should I believe that? Do you understand? Why should I believe that x1 equal to x0 minus fx0 divided by f prime x first divided? Is this what Newton and Raphson one day in the morning wake up and they wrote it? No, right? They did not write it like that way. If someone if tomorrow in the morning, if you wake up and write something and start telling in the Facebook and other social media, this is what I get, the people will not believe, right? You have to give them a derivations, like the way Einstein gave the derivation of E equal to MC square. Okay? Talented people are sitting and all over the world. One after another. Their main purpose, the scientific paper that people are publishing one after another. Someone get something published, then say that, well, this paper got published, let us do these things. Let us change these things and see what we'll get. They said, well, we change these things, we get better performance. And then their paper got published. Understand? And down the road, if you want to be very famous, suppose you will be very famous, okay? Remember, when you go up in the ladder, and you will be under the microscopic investigations by other people. The more you will rise, the more and more. A Georgia Tech professor, he is now making around $600,000-700,000 salary per year. His salary is the second or third. First salary is the president, second salary is the football coach, third salary is. Okay, he did PhD from Cornell University way earlier in 2001, 2002. Very famous. And other university asking him to become their dean because he is consulted with the Bank of America, Wells Fargo, other finance professor. But during the PhD, he published a paper. And now, after 20 years later, when he went that much level, the other people, they targeted his paper and they write to the American Finance Associations, the finding, the paper that got published in American Journal of Finance, which has an acceptance rate 5% or 7%. A paper, if you want to publish in Journal of Finance, this is 7% or 8%. And then the people, they targeted their paper, they did the entire paperwork during his period of time. They said, this is the result. So what he said 20 years ago, that is a lie. How can a person lie in that level? Do you understand what I said? So down the road, if you do the research, whatever research is generated, you say exactly same. Not only that, they email to the university president, provost, and other people, his friend circle. He has now a high level of acceptance. Then they said, so this is our finding. So this is his data. Ask him to come up with a new article. I don't know. Maybe during that time, computer was not like that level. But he showed his frustration. See, I never harm people. I always like people work. And very hardworking person. Very hardworking person. Always and very kind. He's so high level, but person is very kind. Understand? I just emailed him. I emailed him whether he will give me an appointment to talk with about these things. I said immediately he replied, and then I went to him. He gave me his office room, and we had a chat. And one day he took me. I think altogether 3 or 4 times he took me to the dinner, and so I cannot believe his good behavior. So down the road, also always be, even if your friends and other people sometimes got short-tempered or something like, you should keep your temperament cool and be always honest. Understand? So Newton-Raphson method, this is not come up with your idea one day in the morning. There is a derivation for that. Okay? There is a derivation for that. So I'm going to show you that one. So suppose this is what I have. I have a function like that way. Suppose this is says continuous and differentiable. Okay. When a function is said to be a continuous function. When a function is said to be a continuous function. Are you taking mathematical economics course? Who are you taking? None of you taking? So a function is said to be continuous if this f of x limit x goes to 0 plus equal to limit x goes to 0 minus equal to functional value. Function is said to be continuous. What do you mean by 0 plus and 0 minus? Or 1 plus and 1 minus? It is not exactly 0. For example, 0.00000001, right? And then negative 0.00000001, right? Right? And then this is called this is called that. And functional value. The function is said to be continuous and differentiable. This is the continuity. When a function is said to be differentiable, it must be continuous. Like discrete function cannot be differentiable. So now, suppose I have a point in there. In this case, this is the slope. This is the slope. And this is the point. This point comes in here. And I want to put here x of n. X of n. And in this case, suppose this is x and this is y. Okay. In this case, this is the value. In that case, x n plus 1, 0. You agree with this, right? In this case, y equal to 0 and xn is a value. In this case, xn plus 1. Xn plus 1 is just a number, a update. Okay? And y equal to 0, right? And this is a tangent of slope. And that curve is a function. That is the function on which I want to find a solution. Curve is the equation of a function. On that function, I want to find the solution. Are you understanding? That curve could be 5x squared, 7x plus 7x minus 19. I want to find that solution. And this is the tangent. Tangent has a equation. What is the equation? Equation of the tangent is this. Equation of the tangent is this. Y equal to, this is the 12th grade math now I am writing. X minus xn plus f of xn. This is the equation of a tangent. This is the equation of a tangent. Equation of a tangent. So this is the slope or tangent. This is called the slope or tangent. Slope or tangent, right? Slope is now going like that way. Slope can go like that way. Slope can go like this way, right? Slope means what? Rate. How fast or how slow I can go up. That is what called the slope or rate of change. Change of rate, not rate of change. I always mess it up. Change of rate. Now, if I plug here 0, y equal to 0, corresponding to that. Are you understanding? I plug y equal to 0. If I plug y equal to 0, what is the value of x? If I plug y equal to 0, what is the value of x in here? Xn plus 1, right? So now I plug here xn plus 1 minus xn plus f of xn. This. Now, if you change these things, then you will end up with, if you change these things, then updated one, you will get xn minus f of xn divided by xn. You understand these things? This is the update. What they have done, they put two conditions, the functions which we are going to find the solution, that means value of the x. How can I do that? We just construct a tangent over there. On that tangent line, on that tangent that are touching this curve, I want to have plug here 0. Y equal to 0, I put here, then I got like this solution. Then say, each time you will put a new value, you will update this. At certain stage, you will get the solution. More than 400 years ago, it was proposed. Is still now In finance, in math, in statistics, in probability predictive modeling, they are using the Newton-Raphson method. They are using Newton-Raphson method in order to find the solution of the equations, first derivative, second derivative, by numerically. Okay. Now I want to show you, this is graphical explanation. This is graphical. Now numerical example, if you want to take. Numerical example, if you want to take, suppose fx equal to x square minus 4x minus 7. X square minus 4x minus 7. I want to solve this. What is the value of x that will satisfy this equation? Okay. So now if it is x, then what is f prime x? F prime x equal to twice x minus 4, right? F prime x. Now I want to do x1 equal to, let us start x0 with like 5. I want to plug x0 equal to 5. I want to see where it will go and stop. So now I want to put here 5 minus f of 5 divided by f prime of 5, right? According to this formula, right? And then I got here 5.31, 5.33, something like this. And then if I want to do it again, x2, that means this one would be now my guess. That is what I want to put it in here, here, in here. This one, I want to put it in there, there, and there, and then I got 5.31. And if I continue these things, then like this, I got 5.31662. That means I got a stable result. Remember, probability regression, logistic regression, binomial regression, negative binomial regressions, and then Cox regressions, all of these Newton-Raphson. Because beautiful solution by differentiating and then getting the solution is not obtainable. Analytical solutions, beautiful expression of the mathematical format of the solution is not possible to obtain. You have equations after differentiation. You have after differentiation you have equations, but in that equation, the parameter and the variables are mixed up in such a way that they are inseparable. So we have to find the solution by numerical approach using Newton-Raphson method. Okay, now these are all theory. Let me start discussing now mathematical computations. Take a 5 minutes break. Let me bring some more. Okay.
Yeah, I think because of I don't think I agree. Yeah, give. Yeah.
Charger? Yeah, you can charge. Is your?
I didn't know like that. Don't worry. Yeah.
We need a administrator password. Okay. So now we want to do a real life example by using R. Okay. Next week. Next week I will discuss negative binomial regression. Understand? So Poisson regression and negative binomial regression together, I will give you homework next week. Clear, right? So negative binomial regression and Poisson regression, I will do a homework next week. Now I am going to discuss about a real life example. This document I already uploaded in the Western Online. Please read this document thoroughly to understand, because you have seen the theory, right? Now you have to explain by feeding the data to Poisson regression model, when output will be generated, how to explain those results. In this example, there are two covariate and one dependent variable. The dependent variable is number of hours. For example, you are a student, undergraduate student. When you are undergraduate student, suppose one student got 5 awards. What are the awards? He got the best student award. He is the best student for debate. He is the best student for maybe in math. All of this. And some students got 2 awards. Some student 1. Some student got 0 award. Right? So in these data, we want to consider like how the number of awards is affected by the two variables. One is continuous variable known as the math score. If math score is high, the number of awards is higher or lower. Are you understanding? Another one is types of educations the students are enrolled. What are the types of the education? General education, vocational educations, and another one is vocational education, general education, academic educations. Yeah. So by using two covariate, one is type of educations and another one is Another one is math score. We want to predict how many awards each student obtain. Okay, so number of awards is a count data, right? Number of awards is a count data. So that's the starting point. So now let me read the data. Let me go change these things. Okay, go there, download Poisson sim. Okay, now come in here. Install these packages. IO. Let me read the data. Has been read. Data look like this. This is your data. So data has an ID number, but our focus would be on number of awards. This would be our dependent variable, and these two will be our independent variable. We want to predict whether number of awards will go up if the math score will go up. Number of awards is bigger for the academic or vocational or general educations. Those are the things we are going to predict. So in your lifetime, suppose if you want to do research on number of children ever born, suppose you are from what country? Nigeria. So she wants to work with the Nigerian women, suppose 20,000 women data available to her, and number of children, women has number of children, right? Number of children, 2 children, 3 children, 4 children, 6 children, 10 children. She wants to investigate education of the mother, and then age of the mother, and region of the mother. Is this urban or rural? These covariate she wants to investigate to check which covariates are significant to have more babies or less babies. Understand? Do you understand? I discussed two discrete examples when I was deriving these things: number of accident, number of phone call, and here number of awards, right? Now, in terms of this student, I said number of children ever born by women. Okay, so these are the types of dependent variable that you can use in order to feed a Poisson regression model for the data. Okay, one thing I have to explain. Let me explain it before I go. this Poisson regression, before I can forget, I should discuss these things way earlier. This is the Poisson distribution, e to the power minus lambda, lambda to the power x over factorial x. In this distribution, mean equal to lambda and variance equal to also lambda. Variance equal to lambda. So variance formula equal to what? Variance of x equal to expected value of x square minus expected value of x whole square. Poisson distribution you can use when your response variable has approximately same mean and variance. Understand? Poisson regression model you can use when your response variable has approximately same mean and variance. Okay. So when let me write it, when mean and variance of a response or dependent variable, response or dependent variable, when mean and variance of a response or dependent variable are approximately same, we can use function equation approximately same. Understand? So I said like the dependent number of children ever born by the women, right? So number of children ever born by the women. So first woman, second woman, third woman, all of these, suppose 10,000 women you have interviewed. So he has 0 children, 5 children, 7 children, 2 children, 1 children, 6 children, 9 children, 0 children, 2 children, right? So if you find the mean of these and variance of these, if they are same or approximately same, then you can use Poisson regression model. Clear? On the other hand, if mean and variance are not same, you have to use negative binomial regression, which I am going to discuss next class. Clear? Understanding? Okay. Now let us run the R code and get the result. So this is the data. In that data, now I want to change. Are you seeing program is written 3, 1, 3 like this? This level I want to change general, academic, and vocational. Okay. So Control R. So now if you take a look at the data, you see, previously it was a level, now it has been changed. Okay. We change the level of the variable vocational. Now after that, we want to find the summary statistics in here. Okay, as I do not need to write anything, let me do these things now. This is the summary of the P, summary statistics of the P. and then mean for each is obtained. So this is what the mean and standard deviation for the awards we obtain. And this is number of awards, average number of awards with respect to each program. This is the average, this is the standard deviation with respect to. Now I want to take a look at the group bar chart. Group bar chart corresponding to awards number. 0 award, what is the vocational, general education and academic. So this is the bar chart. We see 0 education has the highest one is the academic one. And then also highest number of award stands for the academic one. In this case, no awards for the general and vocational. Okay, this is the way. This is called the group bar chart. After group bar chart, now we want to do the Poisson regression. In order to, you have a question? Anyone has any question? There is no package called Sandwich. Okay. Install dot packages, and then I want to put Sandwich, and then I just want to run this. Now I want to run the functions. Take a look. In the linear regressions, we use the LM, but here we have to use the GLM, generalized linear model. GLM. Number of awards, which is my dependent variable. And then program and math is are my independent variable. This is coming from the Poisson family. That is why I put here Poisson. Negative binomial, you should write here negative binomial. And my data is a P data. Okay? Just one line of code will give us everything, right? One line of code. Now I want to take a look at the summary statistics. This is the summary statistics. Now, these are the parameter estimate. This is the intercept. This is the academic vocational. General one is in the reference category, and then academic and vocational are in the compare category. So reference category means I will compare the remaining two categories with the reference category. If it is greater than 1, then this is better. It's less than 1, then this is not good. And math is this. Now, let me explain something from there. It is the same, but we are computing this lower limit and upper limit of the 95% confidence interval by using robust standard error. So when the assumption? I ask you, read this document thoroughly. Understand? Because when you are going to do the homework, you have to make a comment similar to the comments that you are going to find in there. How the parameters are estimated, how the parameters can be explained. For example, take a look at that. This thing here, this is called the chi-square goodness of fit. If this p-value is greater than 0.05, that means Poisson data fit the model good. This is what mentioned in here. Let me find it somewhere. Here, we conclude that the model fits reasonably well because the goodness of fit chi-square test is not statistically significant. Why? Goodness of fit, this is the chi-square. Are you seeing p chi-square? Deviance, they find the deviance from their residue lower tail. So this line of code they have written, they found this, and as p is greater than 0.05, that means chi-square goodness of fit, that null hypothesis failed to reject. What was the null hypothesis? Null hypothesis is that data fit the model well. And alternative hypothesis is what? Data does not fit. Okay. Chi-square goodness of fit test null hypothesis is data fit the Poisson model and data does not fit the Poisson model. Understand? So the output that you are going to get from the data for your homework, after getting that output, you will have to find like this thing. After finding this, then you have to make a comment like that. Are you understanding? This is just only one document I gave, only one regression I have discussed. Next class, I will discuss second regression, negative binomial regressions. I will give you another document. Your responsibility is to read both of these documents and do the homework by copying these things. How are they making comments? Understand? Okay. Now take a look at that. Some comments I want to make from there. So the coefficient for math, it is mentioned in here. The coefficient for math is 0.07. This means that expected log count for a unit increase in math is 0.07. So this is the way you have to explain these things, expected log count. Later, we are also going to discuss how to interpret the parameter in terms of incidence rate. Later, I'm going to show you. And then now the indicator variable is compares between program academic and program general. General one is in the reference category and academic and vocational are in the compare category. We want to compare. So what is the result? The expected log count for program academic, which is this expected log count for program academic increases by 1.1, increasing by 1.1. Okay. The indicator variable program dot vocational is the expected difference in the log count 0.37 between program vocational and the reference category like this. So here they mentioned like how to explain the parameters. This one discussed like residual deviances approximately normally distributed on the basis of what? On the basis of median. What is the median one? Here, deviance residual. If this median is 0, so that means it is normally distributed. Understand? The comments that have been made in this paper in your report, if I will not find these comments, I will not give you full credit. Are you understanding? So see what they have written in here. In this first bullet point, the output begins with echoing the function's call. The informations on deviance residual is displayed next. Deviance residuals are approximately normally distributed if the model is specified correctly. In our example, it shows a little bit of skewness since median is not equal to 0. What was our median? Our median is this one. So in your case, you will find the median and you will say how your residual behave. Understand? Okay. After that, there is another way. Okay. Take a look what. Sometimes we might want to present regression result in incidence rate ratio. Understand? Sometimes, for example, incidence rate ratio, if hospital receives lot of COVID patients, from there, if we can explain those things in the word of incidence rate, that will be more acceptable. Understand? So that is what they are saying. Sometimes we might want to present the regression results as incidence rate ratio and their standard error together with the confidence interval. To compute the standard error for the incidence rate ratio, we will use the delta method. To this end, we may use the function delta method implemented in the R package. So you are using delta method in here. The rest of these things you have to make it is an exponentiation, x1, x2, x3, x4, all of these, and finally you have to put your m1 and forward m1, which you called before. M1 you already called before. After this, your results will look like this. Now take a look. These values has been changed now. These values has been changed. Are you saying? Previous estimates and current estimates has been changed, right? These values. Now see, the output above indicates that incidence rate for program academic is 2.96 times. 2.96 times the incidence rate for the reference group. Now you can say one is higher than the other. Previously, you cannot say that. Now you can say this. Likewise, the incidence rate for the program vocational is 1.45 times the incidence rates for the reference group, holding the other variables at constant. The percent change in incidence rate of number of awards is 7%. Because of what? Previously it was previously it was 0.07, but now it is 1.07. So that is why they say 1 is the reference category more than 1, so that means 7%. This is what. So when you see this 7%, if you stop, how did they got the 7%? This is actually that one, but 1. So bigger than, you understand, right? So 100%, 107%. So how much bigger? 7%. So that's the reason this 7% is coming for every unit increase in math. For additional information on various matrices in which results can be presented, the interpretation of such, please see the regression model categorical variable like this. And then finally, we want to create a table . Finally, we want to create a table that has been mentioned in there. Please read these things, okay? Read these things. Usually it takes me 3 days to finish grading all of your homework. So don't think that there are 34, 35 students and Dr. Chaudhary is not going to, okay? The students who took classes with me before, they know how each line of code and each line of sentence, what you have written, I immediately, not only that, I read that things, I exactly comment on the grade book. so that it is a documented, you cannot say anything. And then if I sometimes allow you to resubmit those things, then I keep the first comment as well as second comment. You understand? Read these, only one document I have given. I am not going to give you any more document. And all the mathematical derivations I have shown you and give you the code. When I will give you the homework, just new data, and you will use the code to change your I have already given the code. The data will be new. Your responsibility is to replace the data and variable by your variable on the current code. Understand? Finally, I want to do this picture. Okay, this type of picture you want to consider. Here the purpose is, math score is in here. Okay, math score is in here. Expected number of hours in there. I want to compute a like predictive graph compared to the math score corresponding to these three categories. We have seen vocational people, they have a higher curve, expected number of hours when a math score is going up, vocational people. Okay. Academic people, if you take a look, academic people, they have a higher values in extreme right. Okay, extreme right, they have a higher values, academic people. But in this case, that is lower, and this is their curve. So by comparing this graph, you have to make a comment similar to the comments that has been in there. In the output, we see that predicted number of events for level 1 and program is this. Holding math at its mean. So here we can also graph the predicted number of events with the comments below. The graph indicates the most hours are predicted for those in the academic program 2, especially if the student has a high math score. So program 2 equal to what? Program 2 equal to academic. In the above output, we see that the predicted number of events for level 1 of program is about 0.21 holding math at its mean. The predicted number of events for level 2 of program is higher at 0.62, and the predicted number of events for level 3 of program is about 0.31. Okay, now they find the ratio. The ratio of these predicted counts match what we saw looking at the IRR. So this ratio, when they have taken, they got 2.96, 1.45, which is matching with these values, these two values. And this means they created a artificial data for a small scale, and then they predicted those things, and then they found some results, and then by finding the ratio of those estimates, they are getting exactly the same value of the incidence rate ratio. Okay, I think I have now 30 minutes. If you have a questions, we can discuss. If you do not have any question, feel free to leave. But your homework is due by tonight. Right? I got like the cluster people, they already submitted, many of them, but other people submitted homework by 11:59. try to do your homework by yourself. If you do not do your homework by yourself, what will happen? The customized question, right? You know that, right? I declared that. So if you end up badly, then that means you did not do your homework. Do you have anything to discuss? Yes. No, but our findings is consistent in both areas. But we find one by the smoothing, another one by the box model, right? That is similar, right? That is similar. Listen. The reason is that when women got urban women, they got married. No, urban women they got married little late, right? And right after the marriage, they want to pay. Understand? So that's the reason. But the two results is consistent, right? Smoothing result and box model. Yeah. Yeah. That's the same. Yeah. That's the same. No, but it's in rural area, some women organize arguments, right? Like very remote area, there is no monitoring, 16, 17. So in that part, they are biologically very vulnerable. They are not like biologically capable, right? So even though they got married in 2 years, 3 years, they are not, yeah. And then they are with their mates outside work. But in urban area, but right after marriage, they want to have. In general, yeah. Yeah, because yeah, because in order to estimate the dependability, we have to consider managed partners and also using any method. So, yeah. You have a question? Ask.
Hey, Professor.
You have a question, Eric?
Yeah, I had a couple questions about the cluster analysis, specifically questions 4 and 5.
Yeah, did you get the email? Instead of differences, you have to find your thing on the normalized scale. You get the email?
Can I show you what I have,
Yeah,
if possible?
Yeah, you can share. I stopped. I stop sharing.
Okay. Are you able to see the screen?
Yeah,
The one
yeah,
that-
yeah.
So, if I run the dendrogram without truncation, like truncation, because I was in the documentation, it's just a big mess. But if I truncate it, it's more legible. Also, it seems like the clusters are arbitrary, like there's no optimal amount based on like what I read in the book. Is that right to think that, or is there another explanation?
Yeah, I think it is right. So let me explain these things to you. The example that I discussed in the video, as well as the code and the handwritten note that I have provided, you see on that, on that note and code and discussion, there are just 22 components, right? But now I ask you, with the when you delete all of this, there is around all 400 groups. And then I again ask, take a sample of size maybe 100 or maybe 200. Right? So that's the reason you dendrogram may not look like very messy, very ugly. Some other people also contact. But what
So
you
should I remove the truncation then?
no. That's fine. I understand why did you choose that. I understand.
I also I put in what I thought like right around the midpoint. So this one, the cutoff threshold's 8, so that gives me 1, 2, 3, and 4 clusters, and I kind of explained that down there. And then I changed this code right here to do for 4 clusters, and then you just see like a huge list of all the colleges, and then these 3 and their own little cluster.
I what you have done.
Okay. And then I also did normalization for 7, because in the book he uses normalized instead of the D2, he used normalized, so I just included that. And then also last question, did you want both the Jupyter notebook and a Python script?
You give me the Python script and write a short report.
Okay, I have the HTML and it's already written up in the HTML.
So that means you have everything in the HTML that you wanted to give me, right?
Yeah, so I have it written in Markdown.
Markdown. That's fine. If you give me that one, it is fine. You generated it from Jupyter, right?
Yeah, so there was only like a couple of questions I asked specific for specific answers. Some of them I included, like this one. Okay, I think I got it.
Okay.
Thanks.
Yeah. Yeah. And now there is always when like all of the deleted, it comes to data reduces to 400, right? And then I again say take a sample of size 200 or 100 to the results. So whatever you can send. This time I will not do that because of number of rows. Yeah.